So this is problem 11, and let me go ahead and read it. Leuchten star is a star that is located 12.199 light years away. There is a planet orbiting the star with an orbital radius of 0.091 AU. AU stands for astronomical unit, the average distance between Earth and the Sun. Fill in the table below by determining the minimum diameter the objective of a telescope would need to be in order to resolve the planet from the star at the stated wavelengths. And the conversion factors for light year and AU are given, and I should also mention that a light year is the distance light travels in 1 year. Now this is a very real problem. Since 1995, we have been detecting exoplanets, that is, planets that are orbiting other stars. And we'd like to be able to image them, to take pictures of them. And I can't recall, we may have already done that for a select few, but we'd like to do it with more regularity, that's for sure. And so that's what this problem is all about. You know, what kind of equipment do we need? How big a telescope specifically are we going to need if we want to take pictures of these planets? And of course, what you have to be able to do is separate them from the star that they are orbiting. So here's how this works. Up here, we've got our star. There's our star. And we've got the planet, some distance, I'll just put P for planet, some distance away from the star. And way down here, not to scale, of course, is Earth. The distance from Earth to the star, well, in this particular problem, I already know what it is. It's about 12 light years, 12.199 to be precise. But commonly, I would just represent that with an R. And the distance from Earth to the star, well, it's the same distance to the planet. That's going to be roughly the same distance. I know technically sometimes the planet would be ever so slightly closer, but we're on the scale of light years here. So a little bit closer, a little bit further away isn't going to make a big difference, especially when you're talking about the separation when they're going to be roughly the same distance anyway. And this is the angle. That's the angle we need to be able to resolve. And we know the formula to be able to resolve that, right? That's theta min equals 1.22 lambda over d. And d is the width, or we commonly say the diameter because we're usually dealing with mirrors that are in a circular shape. But it's technically the width of our optic, or in this case, our mirror. And if we want to be able to resolve this angle here, if I want to resolve this, then I need a certain size mirror. And so we want to figure that out. Now, it's obviously easy to rearrange this to solve for d. In fact, I can just quickly do that, because that's what we're interested in solving for. And for this problem, we know what the wavelength is. That's told. You've got 5 different ones in the table. And what we're not told, at least not explicitly, is this angle. What's the angle that we have to resolve? And that's, if you go back up to the top of this homework, up in the contents section, the definition of an angle is given. And that definition is theta equals S over R. Now S is called the arc length. And R is, strictly speaking, it's called the radial arm. People often say the radius, but strictly speaking, it's the radial arm. It's the arm you're using to swing out the arc length. So for example, here, the radial arm would be, I'd go from here and I'd be swinging around like this. So it'd be the R, which of course is why I use that letter for this diagram. But this would be it. And so S would be the arc length between the star and P. that there, which obviously is the distance between them. This is S, but it's obviously the distance between the star and the planet. And so you should be able to go through and figure out, okay, what is that angle that I need to be able to resolve to see this planet from the information given. You need to perform the conversions, of course, but you should be able to go through and work it out and figure out what is that angle. And once you know that angle, then you can go through and for the different wavelengths, figure out what size, what diameter objective we would need at the various wavelengths. And what you'll discover is it's large. You need big mirrors in order to see these planets. And that doesn't even take into account the fact that the stars are putting out an awful lot of light, which is just going to effectively drown out the planet anyways. And so there's several technical hurdles to overcome. But the first is just being able to, just having a big enough objective so that you can resolve the star and the planet as two separate objects.